Hi, I'm Ben-Yaakov. This presentation is entitled Ceramic Capacitors Parameters and Lack of Data. Let me start with a short introduction about ceramic capacitors. Now, practical ceramic capacitors are built around either paraelectric or ferroelectric dielectric material. Now, the paraelectric material is a dielectric which is not affected by electric field, it's not polarized. On the other hand, the ferroelectric material is a dielectric that is polarized by an electric field. Now, the name ferroelectric, this name is coming from ferromagnetics. This is the family of materials which are affected by magnetic field. They are magnetized, and they are based on iron, and this is the name ferromagnetic. Now, when the ferroelectric material was invented or discovered, the name ferromagnetic was used, and instead of ferromagnetic, it was replaced to ferroelectric. That is a material which is affected by electric field. So this ferro here is just a carryover. The ferroelectric material has nothing to do with ferro, which is iron. It might have some iron in it, but it's not related to iron at all. Okay, just based on this name of ferromagnetic. Now, practical ceramic materials are built, as I've said, around paraelectric or ferroelectric, and they are actually divided into class 1. This is according to international and national standards, and class 2 and 3 for the ferroelectric material. Now, the predominant class 1 material is a COG or NPO, which is characterized by a low dielectric constant. Now, the capacitance of a capacitor is a function of the area of the plate, the distance between the plate, and the dielectric constant. Now, if this dielectric constant is large, then the capacitance would be large and you can make small size capacitors. If dielectric constant is not that large, then the capacitor will be larger. So the COG capacitors are of low dielectric constant, so therefore they'll be a bit larger. Also, they are limited at the capacitance that you can build practically, and they are not available at very high capacitance value. We'll talk about it a little bit later. Now, class 2 and 3 are very popular. These are the ferroelectric materials, and they have different kinds like X7R, Y5V, and many others. And again, they are of high dielectric constant, so therefore you can make very small size capacitor with large capacitance. And they are, as I said, very popular, small, and relatively inexpensive. Now, the capacitor can be built as a single layer or a multi-layer ceramic capacitor, and like other capacitors, it is also temperature dependent. Now, here is a sort of a overview of various kinds of ceramic capacitor materials. These are EIA and JAC, stand for the Electronic Industry Alliances and Japanese Industrial Standard. These are standards for the size, temperature range, etc., that are assigned to capacitors. And this table stresses the point of temperature. And I should say that in many cases, a designer looks primarily at this data. That is, how much is the capacitor changing over the operating temperature. This is the operating temperature of this particular capacitor, and here is the change. This one is a much larger one, this X5T, plus 21% to minus 33%. This is now shown here in sort of a graphical way. Here are the different, this is temperature, this is the percent change. 0 means the nominal value. Now the COG practically doesn't change. It's a very stable capacitor, and the changes are very small over temperature. But the class 2 and 3 do change quite a bit. For example, F, of course, changes a lot, down to minus 70%, 4 up to 75 degrees. That's not that much. The X7R is very popular because it's sort of a compromise. It changes, but not very much. I should say, however, that the temperature dependence of the capacitance is not the most important parameter of a ceramic capacitor. And the fact that many designers are really looking at discharge as the most important part of the characterization of the ceramic capacitor is in effect a mistake, because there are other effects which are perhaps more important, and we'll talk about them a little bit later. So, in a way of introduction, let me just continue that the losses are due to the RMS current passing through the capacitor. Now, the losses of ceramic capacitor are frequency and temperature dependent, and also there is a nonlinearity in two aspects. There is a nonlinearity due to a DC voltage bias that will be imposed on a capacitor, and also there is a nonlinearity due to AC volt excitation. And the nonlinearity is a function of the amplitude of the AC volt which is imposed on the capacitor. This is something very specific to ceramic capacitors, and we'll talk about it in detail later on. Now, manufacturers do provide some data on ceramic capacitor. Unfortunately, a lot of data is missing, and therefore it is rather difficult to choose a capacitor for a particular application because there are very many parameters and a lot of data is missing. Now, I should also add that the behavior of a ceramic capacitor is very peculiar. It's a very strange component, and it behaves unlike any other electronic components. It's kind of a weird phenomenon that we can recognize, and I'll talk about it a little bit later. Let me start off, however, with the very basic parameters of just any capacitor, linear capacitor 2. Now, we, of course, specify the capacitance in farad. There's a maximum voltage in volt, maximum temperature for operation, and then the ESR. This is a key parameter, the equivalent series resistance, and it is based on the very simple model that describes the capacitor as a capacitor plus a series connected resistor. Now, this is, of course, just a model. It's not a real resistor, and it stands for the losses, the electric losses in the capacitor. Now, the value of this ESR is either given, or many times it's given in a sort of a hidden way as a dissipation factor. Sometimes only dissipation factor is given, sometimes both of them, sometimes only ESR. It's not consistent. Now, what is a dissipation factor? Dissipation factor here is in fact the ratio between the resistance of the real part and the reactive part of the capacitor. It's also equivalent to times delta. Delta is the angle between these two. So, since the reactive value is 1 over omega c, then, or 1 over 2 pi f c, then the dissipation factor is in fact omega c ESR, and therefore ESR can be calculated as the dissipation factor over omega c. Now, it's very important to realize that this omega is the omega at which this dissipation factor was tested. Now, normally it is 1 kilohertz, so it has nothing to do with the operating point of this capacitor. You might run it at 100 kilohertz, but it was measured for the dissipation factor at 1 kilohertz. Okay, so you need then to find out how is this dissipation factor affected by frequency. this doesn't tell you all the story at all. This ESR that you calculate here has really very little to do with the ESR that you need for your design at a given frequency. However, if you know the ESR at the operating point, then of course the power dissipated will be I squared times ESR at the operating point. So these two are not equal. Now, another parameter that is something given is the maximum ripple current uh, that is allowable for a given temperature rise, okay? And then maximum pulse current allowable before destruction of the device. It's in amp, and sometimes also the duration of this spike, allowable spike is given. And then there is the aging information, like how much the capacitance usually is dropping over time, and it is normally given as percent per decade hours, okay? And a typical value is like for a ceramic capacitor, like 2%. Now, there are extra parameters that are unique to the ceramic capacitors, which I'll just point out. We're going to go over them in very much detail later on, but just let's have an overview here. The capacitance of a ceramic capacitor is dependent on the DC bias voltage. And then the ESR is dependent on temperature and frequency. And then the capacitor is also a function of the AC volt excitation, or the amplitude of the AC volt excitation. And the ESR is also dependent on the AC excitation. So if you have a capacitor which is operating in, say, a resonant converter, which is exposed to AC voltages and current, then both the capacitance and the ESR will change as a function of the amplitude of this excitation. So there are many more. We are going to talk about them in this video. Now, for a overview of a ceramic capacitor, I really recommend the Wikipedia link here. And there is a lot of information there regarding the type of capacitor, the materials, etc., etc. Now, let's have a look, first of all, at a typical ceramic capacitor datasheet. Of course, there's no endorsement here. I'm not affiliated. This is a TDK datasheet. I have nothing to do with the company. This is just an example. Okay, so this is a typical page, front page. This is the designation of the capacitor. It says the size, temperature, etc., the material. We are not going into that. And then let me just point out, however, that this whole information is given for a particular application. And the application is like, say, a buck converter or a converter in general, in which the capacitor is such capacitor which is being used, capacitor being exposed to a DC plus an AC ripple. So all this is given for this particular application. In this case, you'll have a DC bias, here the DC bias, and then an AC ripple on it. And of course, through the capacitor, you'll have an AC current, no DC through the capacitor, just an AC current. And this information is related to this situation. Now, let me just go over parts of this datasheet. Let's say here, this is the dimension, 4.5 millimeter times 3.5 the width, and thickness 2.3. It's a small capacitor. This material is X5R. This is the temperature range, and this is the capacitance range, but this is for no DC bias of the capacitor, okay, 0 DC bias. The rated voltage is 250 volt. This is not AC, this is for DC. For AC, it's a different story. Capacitance is given, it's 0.47 microfarad. Again, it's nominal, 0 DC, and it is for small ripple voltage. Now, capacitance tolerance, that is the variation from one unit to another, is 10%. This again, all nominal values, no DC, etc. And dissipation factor, we already talked about it, 3%. This is again for 1 kilohertz test signal, and 25 degree nominal, etc., etc. 0 DC bias. So this is one point for the dissipation factor that in fact you can do very little with it. And then insulation resistance, this is a DC resistance. The leakage is very small at 1 giga ohm. It's practically an insulator. Now let's have a look at the graphs now, first of all. Now this graph is based on the extended model and also a simplified model of a capacitor, which now includes not only the capacitance, ESR, and also the inductance. This is inductance of the interconnection and inside the capacitor in between the plates. And this is called the ESL, equivalent series L, and this will be equivalent series resistor. Now this structure has a resonant frequency. This is the angular resonance. This is the frequency 1 over 2 pi LC. This is LC. And at resonance, of course, the reactance part are canceling each other, so you are left with ESR. And at frequency which are below resonant, then the ESL impedance is very low, and you see the capacitor, which is the highest impedance here as compared to these two. And at frequencies above the resonant frequency, you see basically the inductance, because this is the low impedance and this is also low compared to this impedance. So at low frequency, the impedance is like 1 over omega C, and at high frequencies, it's omega ESL. Now, how it is represented in a graphical way. This is frequency in a log scale, and this is the impedance in a log scale. So in a log scale, 1 over omega C is a straight line. And we see here how this impedance is going down as the frequency goes up. And above resonant, we see omega ESL, the impedance going up again because the capacitor is sort of a short. Now at this particular point, which is the resonant circuit, the resonant frequency, here it is, resonant frequency, this is the ESR, and indeed we do have a separate curve now for the ESR as a function of frequency. And as you can see, at 1 kilohertz, at which the dissipation factor is measured, the ESR is very high, and it's going down. And say for the range of say 100 kilohertz to 1 megahertz, this is where say power electronic circuits do operate. It's pretty low. Okay. In fact, at 1 megahertz is going down to about 10 milliohms for this particular 0.47 microfarad capacitor. And of course, these two coincide now because at the resonant, this curve here, the impedance is ESR, and this is ESR, so these two coincide at the resonant frequency. Now here we see the dependence of the capacitance on the frequency, and as we see this particular capacitor, it's pretty constant, doesn't change much except for the region of the resonance, which is not an operating region. We would operate up to say 2 megahertz or 1 megahertz for this particular capacitor. Now we have another graph. This is entirely characteristic of ceramic capacitor. You don't have it in other capacitors. And this is how the capacitance is dependent on the bias voltage. So this is measured by adding a AC excitation, small excitation. Well, each company is using its own value. I'll say it will be between 0.1 and 1 volt. And so for the various bias voltages, these bias voltages change. The AC voltage and the current of the capacitor are measured, from which the capacitance is calculated. So this is sort of a ripple capacitance, the derivative capacitance for a given bias voltage. So we see here that it starts at 0. This is a change in percent, and this is the bias voltage. This is a 250 volt capacitor, so it goes up to 250. And as you can see, this capacitance goes down dramatically. It goes down to 80%, so only 20% of the capacitance are left. We start with the 470 nanofarad, and at 250 volt bias, it's only 94 nanofarad. It's a big change. Now, here is the temperature dependent. We talked about it earlier, and we see, first of all, the temperature dependent for the capacitor at zero bias voltage. This is the red one, zero bias voltage. This is this point, in fact, and you see some changes, which are a few percent for this capacitor. And then we see the temperature change when it is already biased, and when it is biased to half of the rated voltage, then this is 125, half of the 250. It's already 55% down. Here it is, 55% down, and the temperature change is small. So as you can see in this particular case, the temperature changes are really small compared to the huge change of the capacitance as a function of the bias voltage. Now, another parameter which is very important is the allowable ripple current, and this is given as the ripple current here and the temperature rise. You can see what is the temperature rise as a function of the ripple current passing through the capacitor. Now, these are three curves for different frequencies. This is 100 kilohertz and this is 1 megahertz. And as you can see, 1 megahertz is better. You can go to much higher current with the same temperature rise, say 15 degrees. You can go up to about 2 amp, and here a little bit above 1 amp. Now, the reason for this difference is that ESR is changing with frequency. These are for different frequencies. At 100 kilohertz, the ESR, this is 100 kilohertz, ESR is 30, say, milliohms, and at 1 megahertz, it's already 10. So therefore, the heating at 1 megahertz is lower than it is at 100 kilohertz, and therefore you can pass a higher current at 1 megahertz. Let me just say that the temperature rise is a function of the power dissipated. This will be the I square ESR at the operating point. And the increase in temperature is a function of this power times the thermal resistance. That is the thermal resistance between the element here, the capacitor, which is soldered on the traces here. And this thermal resistance is a function of the layout, actually, because these traces are acting sort of a heatsink, and therefore this should be specified for a given layout, okay? Because if the pads would be much larger, then the power dissipation could be even better and the temperature would be lower. Now here's a good point to explain something that I think baffles many engineers, and that is that in many applications you'll see that the capacitor which is put on a bus voltage, on a bus line, will be composed of two capacitors in parallel. One, a big one, say 10 microfarad, and 1.1 microfarad. They are used in parallel. And the question is, well, if you have already 10 microfarad, why do you need another 0.1 microfarad? Well, the answer is that these two capacitors are for different technologies. This could be an electrolytic capacitor, and this would be, say, a ceramic capacitor. Now, an electrolytic capacitor will have an ESL, an inductance larger, and therefore the resonant point will be lower. So here it is. This is the impedance of the 10 microfarad capacitor, and this is its resonant point. And beyond this point, it's becoming inductive, okay, going up. Now, the 0.1 microfarad ceramic capacitor starts with the impedance which is much higher because it's much smaller. It's 100 times smaller capacitor, so it's a 100 times difference here. And then it goes down. However, since it has a lower inductance, Then the resonant here is at much higher frequency, and it goes here, and then it goes up. So if you look at any frequency here in between, you find something of very interesting. Here, for example, you see that the impedance of the zero point 0.1 microfarad capacitor is much smaller than the impedance of the already inductive 10 microfarad capacitor. So at this region, the 0.1 microfarad is actually operating, while this is sort of a non-affecting the circuit anymore. So this is the reason why you put these two. So these should be of different technology, and this one should have a resonant frequency which is much higher than this one, otherwise it wouldn't have. Now let me recap about the classes. We have the class 1, which is the best one, NPO. It's temperature stable. However, it has low dielectric constant, so it'll be, they call it low volumetric efficiency, which means that the size will be larger. Now, then we have the class 2 and class 3, which are ferroelectric dielectric based, and these have large dielectric constant, so therefore they can be made small and with large capacitance. Class C has the highest dielectric constant, the largest. However, it is sort of least stable, and it is sort of obsolete now. However, there are many capacitors on the market which are the class 3. Here is another view of these three groups. This is the class 1, class 2, and class 3. These are representative COG, X7R, and Z5U. And here you see what is really happening. This is now the change of capacitance as a function of temperature. And you see that, well, there is a drop here, but look at the scale. This is percent, so this is like 0.15% between minus 55 and 125. So it's very, very stable. Now compare it to the X7R. Here we see the change, and the scale, however, is much different. We are talking about 10-15% here, and it goes down to minus 15%. And the same thing, by the way, goes for the dissipation factor. You see here it's fairly stable, while here the dissipation factor is also changing. Interestingly enough, dissipation factor of X7R is going down with temperature. So there is the advantage of operating them at the elevated temperature, because then the losses will be lower, the ESR will be lower. And of course, we have the Z5U. Again, these are large changes. The scale here is much larger. Also, the value of the dissipation factor of the COG, this is in percent, is very low. It's 0.1, 0.2, meaning that the ESR will be small. We'll see it in a minute. And here, the dissipation factor is in the percent, 2 to 3%. Now, looking at the impedance chart here, and again, this is the impedance, this is the frequency, this is for the COG, this is for the X7R. And of course, you have to compare two capacitors of the same value, because the larger the value, the smaller will be the ESR, because you are sort of connecting in parallel capacitors. So let's look at 0.01 and 0.01 here. Let me just restate that for the X7R, you can get commercially much larger capacitances, but you are pretty much limited with the COG. It goes up to, say, 0.1, 0.2 microfarad. So comparing the 0.01 here and 0.01 here, this is the ESR. You see it's 10 milliohms for this particular capacitor, okay? The ESR judged from this plot at the resonant frequency. Now, if you look here for the X7R, it is much higher. This is already 200 milliohm. So you see that the COG has many advantages, but as far as stability goes and lower ESR, but again, size-wise and availability of large capacitance, there is a problem here. Now, you would have thought that that is the story about the change of capacitance, but it's not. There's more to it. This is a copied from an article by Maxim Integrated. There's no endorsement here, just taking it as an example. Many other companies are giving the same information, and they are talking about the change of capacitance as a function of size. And indeed, let's have a look at this chart, which is really amazing. Um, these are for two capacitors or two values of capacitor, 1 microfarad and 4.7 microfarad. Both are for 16 volt, X7R, X7R. Let's concentrate on 1 microfarad capacitor. So here we have the 1 microfarad, and this is also 1 microfarad, these two lines here. And these two different in the size, okay? This is this size here, 12.6, the bigger size. This is somewhat smaller size. But then we have another 1 microfarad capacitor, but of much smaller size, 0.603. And lo and behold, you see that although the material is the same, capacitance is the same, voltage is the same, this particular capacitor, which are the larger size, changing very little or much less than this particular one, which is the smaller size. Now, the reason is that to get a smaller size, you need to pack the material. You have to actually live by a much higher electric field strength so that the electric field imposed on the electric material is much higher, and therefore it will affect the change with voltage. Okay, so it's not only the voltage, it is the voltage and the package, and we'll see there are some other reasons for a change. This is another company that showed this same information. Again, this is same capacitor here, 10 microfarad, 10 volt. So B is a Japanese notation type. And these are different sizes. The 2.7 millimeter, this is 0.95 millimeter. And you see that the thin one is changing much more. These all are 10 microfarad, 10 volt. Now, if you compare 10 microfarad, same material, but different voltage, maximum voltage, you see also a much different behavior, which is kind of strange. You would expect that the 16 volt will be like the 50 volt, except that it'll stop here, so it'll be something like this. But not in this particular case. This is not typical. I mean, capacitors, ceramic capacitors are behaving differently from manufacturer to manufacturer, from package to package, so you have to be very careful about it. So, however, in this particular case, you see that in this case, the 16 volt goes like here, while here, this is the maximum voltage. It's 55%, while this one goes to 90%. I mean, it's only 10% is left of this capacitor. So 1 microfarad here as compared to the 10 microfarad here. Now, TDK has introduced a new type of capacitor. They call it the Ceralink capacitor. The name comes from the fact that it is intended for the link or bus capacitor for capturing ripple current. Size is not very big. It's like 10 millimeters times 8 millimeters. But see here, the currents are very high. You can pass them 11 amp and 9 amp in 1 unit. And however, there's here this little one here, and this is a footnote. And let's see what it says. It says the normal operating current without forced cooling is 150 centigrade. That is, you can get this current only if you operate this unit at a very high temperature, approaching 150 degrees centigrade. And we'll see the reason for it in a minute. So there's a catch here. You have to operate this unit at very high temperature. Now, here are the curves for this particular capacitor, which is behaving entirely different. I see that let's have a look at the capacitance change as a function of voltage. See these curves going up, in this case, not going down as before, going up and then down. The difference between these two, between these curves is the temperature, okay? And here we have another cut here. This is again capacitor change. This is temperature, and now this is the DC bias. This was DC bias or capacitance change as a function of the DC bias, and here is capacitance change as a function of temperature for different DC bias. So the 400, here it is, 400 volt. This is the unit, and you see a big change with temperature. 400, this value here is the nominal value, and this is the change below and above this value. And if we look now at the dissipation factor, it's also a big change. This is now a function of voltage, bias voltage. And you see that you get good numbers for the blue one, which means 125 degrees centigrade, okay? The black one, which is 20, or say the red one, which is 25 degree, here it is, it's not very good. At these voltages, it's high, very large dissipation factor. Or here we can see it in another cut. This is the dissipation factor as a function of temperature, and we clearly see that in order to get a low dissipation factor, you have to operate here at very high temperature. And this is the same, of course, for ESR, which is a derivative of the dissipation factor. And let's go over here. This is the ESR as a function of temperature, and this is for different bias voltages. And you see here that, again, of course, the ESR is low only at high temperature. At low temperature, it's not so good. Now, there's a paper that has been published recently in the PCI Europe conference in Germany by a group from Spain. Actually, there's a guy from Germany. And they have actually tested many capacitors. These are ceramic capacitors. This is a film capacitor. This is a polypropylene capacitor, which is the best AC capacitor available. And it is, however, much larger than the ceramic capacitor. So whenever you look for small size, you have to go to ceramic capacitor. This is also ceramic capacitor, while the film will be larger. Also, there is a cost issue involved. These are more expensive. Now, also shown here the Ceralink, and the performance is very poor here. You see, here we have, say, of these ceramic capacitors that's concentrated in this group here. We have 20 amp. This is for a 5 microfarad total capacitance. It's a bank of capacitor, and they are biased at 350 volt. Okay. Now, here we have this, say, increase of 30 degree, and you see that you get 30 degree already at 3 amp with this Ceralink. But as we have seen before, the Ceralink performance is optimized for high temperature. So you really have to keep going before you'll see a benefit of this capacitor. That is, at 60 degree above ambient, this ESR of the Ceralink is very poor. So therefore, the dissipation is very high. And you have to go to very high, as we've seen, 120, 150 degree to get the benefit of the low ESR. Now, if you have thought that this is complicated and bizarre and too many parameters and too many dependencies, well, wait until we talk about the AC behavior of the ceramic capacitors, which is even more complex. Now, in application like resonant converters, you really expose the capacitor to an AC voltage and an AC current. Well, say it's a sinusoidal wave here and here. Here we have a square wave resonant circuit. This sort of represents a resonant converter. This is the representing the load. And so the capacitor is exposed to a AC current and AC voltage. As it turns out, the behavior of this capacitor, the ceramic capacitor in this situation, is really entirely different. Okay, so let's have a look here. Let's take an example, Murata. Again, no endorsement implied. This is a 4-volt capacitor, X7R, 1 microfarad capacitor. And we see some similar parameters we talked about, but there's here a new type of a graph, which, by the way, Murata is one of the few companies who provide it. Other companies even don't provide this information. Okay, so what does it say? It says here capacitance change, or capacitance value in this case. One is the nominal value, and this is AC volt excitation. That is, the capacitor now is exposed to an AC signal, no bias, like in the case of a resonant converter, say, and the amplitude of this AC is changing. Okay, here it's a 0.4 volt, 0.8, 1.2, up to 2 volt. This is a 4-volt capacitor, 4-volt DC capacitor. Now, we see here that at small excitation, small AC voltages, the capacitor is very small. And it's becoming larger and larger as we go up and up. This is for 25 degrees, the same temperature, no bias, and this is just dependent on the amplitude of this excitation. Now, this curve here is the one we talked about. Here we have a DC bias, small perturbation, and we measure the local capacitance. Okay? Now, Murata is doing this measurement with the 1-volt excitation. So 1-volt excitation here, 0 bias, corresponds to 0 bias and 1-volt excitation. We know that they are using 1-volt excitation. So this point and this point are actually the same point. But for no bias, lower amplitude and higher amplitude, you have different capacitances. Okay, and we see here up to 2 volt. This is again a 4-volt capacitor. Let's have a look at another capacitor for just to get the impression of what is really happening here. This is a 0.3 microfarad. It's again Murata, 500-volt capacitor, X7R again. And here we see again this curve. This is dependent, now it's a high voltage capacitor, so they can drive it at high AC voltage. This is AC voltage only, no bias. And in this particular case, the change is not that big. It's like 0.3 to 0.33, and that, however, it goes down. Okay, it goes down here. Now, leaving alone the question of the sensitivity to AC, there is a major problem here from the theoretical point of view also, because if you drive a capacitor with a, say, sinusoidal waveform, say the voltage is sinusoidal, well, that's as sinusoidal as I could draw here. Now the current will not be sinusoidal if it's a nonlinear capacitor, so it'll be something like this. Now you take this value and take this value and you calculate from here the capacitance. Now, if this capacitance is for the same frequency, this should be sinusoidal and this should be sinusoidal. And however, here you have a distorted waveform, at least one of them. If, however, there would have been a resistor here, this would also be distorted. So what does it mean that you take two values and you divide? It's not the first harmonics, it's just the RMS probably, or maybe the rectified and averaged. So the whole question of capacitance is really questionable from the theoretical point of view. However, it gives you a measure of really what happens as you change the excitation of this capacitor. Now there is another issue here, and that is the fact that when you drive this capacitor with a high voltage, like here, 120, 160 volt, uh, the current will be high. This is a zero point 0.3 microfarad, 0.33 microfarad capacitor. So let's assume that you are driving it at 200 volt, just for getting a round number. Okay, assume that VAC is 200 volt. Now the current that you will pass will be, here's the current, V omega C, 200. This is measured at 1 kilohertz, by the way. I didn't say that as yet, which is another story altogether, because we don't know what happens at 10 kilohertz or 100 kilohertz or any other frequency. This is just given for 1 kilohertz. And so the current will be 2 pi 10 to the third 200.33 microfarad. And it comes to be 0.4 amp. Okay? Now this is driven at 1 kilohertz. And at 1 kilohertz, the ESR is very high. It could be in the range of 1 to 2 ohms. So the power dissipation of this element while being tested is 0.4 to say 4 watts, somewhere in between. So it's going to heat up. So this 25-degree doesn't say much. Maybe it's the ambient, or even if they'll put the capacitor into a bath of oil, which is kept at 25 degrees, the inner capacitance, I mean the inside the capacitor, the temperature sure will be high. So this curve doesn't say really much, just give you an indication that something is happening when you change the amplitude of the AC excitation. Now, this is another look at the same problem. This is by the Cornell Dubilier company, just giving another view of the changes. Again, no endorsement implied here. This is for two capacitor X7R and Z5U, and this is much higher dielectric constant. And what we see here, this is now in the same curve as we've seen before. This is percentage change of the capacitance, but here it's a logarithmic scale. So this is why the curves look a little bit different. So this is the DC case. That is the DC bias with AC ripple. So this is the incremental or the ripple capacitance and the change of the ripple capacitance. You see that as you go above, say, 20 volt, the capacitance starts to drop. However, for the AC excitation, no DC, just AC excitation, it's going the other way. It's becoming larger, and at 20 volts, it's actually 15% or 20% higher, actually 15% higher than in the low excitation voltage. So it's really going up. Now, the same thing goes for the dissipation factor. It's also affected by the this is the DC effect of the DC bias, and this is the amplitude of the AC, okay? And you see that the amplitude of the AC will change the dissipation factor quite a bit. I mean, we're talking about between, say, 1 to about 4, but it's quite a bit of a difference at this range of excitation. So what we have here is that the characteristics and the parameters of the capacitor are changing as a function of the amplitude of the AC voltage that you are imposing on the capacitor. The company by Johnson has introduced a capacitor which is intended for AC power application. This is a ceramic capacitor, but they're saying it's optimized for AC application. Okay, so let's have a look at the data they are providing. This is the same data we talked about before. However, the excitation they are using is much higher, so we can see the complete picture here. So this is the capacitance as a function of the AC voltage, no bias, and we are talking again about X7R. This is just talking about one particular capacitor. There are many other kinds, and they behave differently. Okay, so let's have a look at the X7R again. Now, the difference between these two is these are capacitors which are rated for different voltages. This is 50, 100, etc. So let's have a look at the 50. Okay, here it is. So what we see here that as we increase the amplitude of the AC excitation, the capacitance is going up to 30%, and then it starts to drop. Part of it may be, by the way, due to heating. I don't know, but anyhow, that's what we see here. Go, and in fact, it go almost back to what it was. But this is a very high drive. This is a 50-volt capacitor, and this is sort of an overdrive here because the AC here is what 60, 70 volt. And similar behavior you see for the different voltage rating, capacitor with different voltage rating. Now, as we have seen before, this also affects the dissipation factor, which is going up quite a bit. Here, it's only 15, 18%. In the previous slide, we've seen changes between, say, 1 to 3%. So it's a factor of 3. And here it's only 20%. So you really don't know what's going on. It's really strange that there's that much of a difference between two sets of data for this X7R. So what can we learn from all of this? It turns out that choosing a capacitor or AC application is not an easy task. It's very complex and it's really complicated. You need to, of course, define the capacitance you need, the operating AC current, and then you have to determine the maximum ESR that you can allow, depending on the dissipation that you can allow, etc. Now, from this, you need to know what is the operating DC voltage. By the way, the information we got here is no DC. Now, what happens if we have both large AC excitation and DC? Well, there's little, if any, information about that. So then you need to know the AC amplitude, and then you go through various capacitors and try to match the ESR to the one that you need under all these operating conditions. Now, obviously, you'll have to iterate because there's no chance you'll find it immediately. So you try one, another one. And I think that in most cases, for the AC application, you'll have no choice but really test the capacitor just to see that it really holds up to the expectation. Now, this is just a question of power dissipation. There are a question of nonlinearity effect. Keep in mind that the waveform could be distorted, and in some applications, this may have an implication. So this is something else that has to be taken into account. So this brings me to the conclusion. We see that ceramic capacitors are really poorly specified, especially for large AC voltage excitation at different frequencies and at different bias voltages. All the information we have, very scarce information, is for zero bias and 1 kilohertz. Now, application of ceramic capacitor in resonant converter needs really careful design because there's very little data. Now, high dielectric constants are less stable. We've seen that they are prone to changes, etc. COG or NOP is the most stable, and it's a very good capacitor, but it's really limited. So in one package, you cannot get more than, say, as of now, more than about 0.1 or 0.2 microfarad capacitance per package. So if you need large capacitance, then of course you have a problem. You have to build a bank of capacitors if you like really to use this stable material. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it interesting and it will be useful to you in the future. Thank you very much.